speaker, Yuji Odaka, who is from Kyoto University. He's visiting Imperial College, and he's visiting Simon Center now.
Yeah.
So he will be talking about the Castability and the algebraic geometry.
Yeah, so thank you very much. So as the title shows, I'm going to talk about algebraic geometric aspect of Castability. So, or maybe algebraic geometric aspect of Castability, I would say. Actually, this title is suggested by Radu, not myself. So I'm just following it. So I think I'm going to talk about the relation with some other fields in algebraic geometry, such as birational geometry and the modular theory. So as the earlier talks show, is Castability, the notion is well, maybe I cannot simplify too much, but it's actually well, it's coming from a metric problem or like canonical metric problem, especially as Claude's talk showed. And so what I'm going to talk is the relation of this notion with other fields, such as birational geometry, birational geometry, so which is a field of algebraic geometry, and other fields. Oops. Oh, moduli. So personally speaking, I'm quite algebraic guy, and I started with this kind of things from the. Originally, I have been focusing on classical GIT stability notion for varieties, and at some point, I noticed that well, maybe this Castability is well, better suited for studying stability of varieties in various sense. Then I started to focus on this stability, and then then I noticed that well, differential geometry people were very much developing this connection with metric, and then like so I'm coming from the kind of opposite way. So originally the stability notion, classical GIT stability notion, is coming from the modular theory, so it's coming from this side, and also like. So anyway, so let me mention this. This birational geometry is what I mean by birational geometry is mostly based on minimal model program. So this is quite different field, and well, people often abbreviate this as M and P. And well, today so in this talk, I think I will focus on this relation with birational geometry, and maybe a bit, well, at the end of this talk and the next talk, I will talk about more on the modular side. So, well. Yeah, so okay, so let me start from the background of birational geometry. So I know that the audience are from several areas, so please feel free to stop whenever you want by asking questions. So this minimal model program is some kind of program which simplifies a given variety by Bayesian construction. So which, roughly speaking, studied in around 80 or something. And still very much developing. It's to name a few: Mori, Reed, Kawamata, Kora. I think I cannot write everyone, but a remarkable theorem which recently appeared is in 2006. The preprint appeared in 2006, which is by Brook, Cassini, Hekon, Makana. So before this, the theorem was for up to 3-dimension or at most 4-dimension variety. But from here, or a bit before the Hekon Makana's result, I established this minimal model program for arbitrary dimension, so higher dimension. But it's not settled in full generality, so there's some issues still now. But anyway, so what's this program do is, so given a projective variety, X, then we proceed. We do some Bayesian construction or finitely many times, and then we get some simpler, object, which is called minimal model, or Mori vibration. So this, each one step is either constructing divisors, or what is called flip. So it's a bit hard to explain what is flip, but it's a birational morphism which is isomorphic in codimension 1. So we are not contracting divisor or extracting divisor. So this doesn't happen. For example, this doesn't not exist for dimension 2. I think as this is a school, I should actually give some details. X is actually in most of cases, X is supposed to be normal, and Kx is Cartier. Q Cartier, sorry. Which means if you multiply by some positive integer, then it becomes some Cartier divisor, which means it's locally defined by one equation. And this is to make Kx tractable. Or there's some, or maybe sometimes we also discuss non-normal variety, but still reduced Gorenstein codimension 1. Well, Gorenstein means this Kx is, more or less, this Kx can be properly defined as a line bundle. And cell condition 2. Which more or less means we cannot get some cover, which doesn't, which preserves away from a codimension. So this means that this means x. So if you take open locus and then some closed subset with a closed subscheme with a codimension bigger than 1, then this function is the same. More or less like this. So anyway, so like for example, if the x is normal, then this condition naturally satisfies.
This is called semi-normal.
It's a bit different. It's a bit different. And kx is Q Cartier. Why we need this Q Cartier condition is we often, from now on, we usually often pull back the kx to some resolution and other varieties. So we need to define what is the pullback of kx. And in Cartier divisor case, as it is locally defined by one equation, it's easy because we can just pull back the local equation. So anyway. Okay, maybe I write here. So so for dimension 2 case, this is due to Italian school. In maybe late 19th century and early 20th century. And in this surface situation, we can, as probably most of you know, that we can leave this x smooth. I mean, if you start with smooth x, then what you do is you found some rational curve with self-intersection of -1, then you contract that. Then the contracted variety is still smooth, and we can work in a smooth category. But a main difficulty in higher dimension is that, as far as you're working in a smooth category, the minimal model program doesn't exist. So I think that's the reason people didn't develop for quite a long time. So we should work in multi-singular. Singular varieties class. So indeed, even if you start with a smooth threefold, let's say, then maybe the x1 is already has some mildly singular, mild singularity. So the minimum model doesn't exist in general.
Can you remind us what the minimal model is when it exists?
Yeah. So the formal definition is this kx is nef, which means for any curve C inside x prime, in this case, the degree of this kx is less than, at least 0, and non-negative. So it means that kx prime is sort of non-negative. Yeah, and maybe I should have also mentioned what is modified vibration. Well, this is not really the same, but it's more or less a fan of vibration. So here you have X vibration structure, right? This with a general fiber fan, well, fan variety. So for example, a projective bundle is a Mori vibration.
All these varieties in the sequence, they are projected.
Right. So what you do is like you take some specific linear series and then proceed. So yeah. So in higher dimensions, so I mean the dimension bigger than 2, it's the thing is very difficult in general because the singularities rise up. But there's a good news that we can we have a good invariant of singularity. Whoa. Good news is that this MMP steps will keep an invariant of singularity or called discrepancy. So what's that? So well, it's defined in terms of blow up of X. So if you start with a singular variety X, then you do some versional blow up, or maybe resolution. Or suppose, well, in this case, suppose this is resolution of singularity. I mean, this is birational, and also this is smooth. Or such a thing exists due to Hironaka in characteristic 0. And we can compare canonical divisors here and here. Then if you suppose this is smooth and we do some further blow up, which is still smooth, then what we can see is at least this difference is positive. So if this is smooth, then we can see that this is, well, this which has a support inside the exceptional locus. And well, if X is smooth, then this is always smooth, positive. And then, so the idea is to define a class of singularities like that, or maybe a bit broader class like this is at least -1 or something. And this is called discrepancy because this is the discrepancy of canonical divisors. And well, good news is that this discrepancy doesn't get worse in this MMP step.
But this depends on the resolution.
Yeah. So but each divisor, so this is an invariant of divisor's class, and also the variety. But if you fix a divisor, then it's well defined. I mean, if you take further blow up, then it just change. So by using this discrepancy, this invariant, let me define the important class of singularities. So why I'm doing this is it will be important also in the study of Castability. So the following class of singularity is MMB closed. So, actually there are many more singularities class than I write here. I'm writing here. Let me just write 2. So one is called log terminal, which is like every discrepancy. Maybe I can introduce symbol like this. So this is AI. This means for any exceptional divisor, A, B, this is bigger than -1, and X is semi-log canonical. If this is like this. So this is quite an abstract notion at the first sight, at least. But I think maybe most of you haven't taken, but I'm distributing a paper, you know. So basically, what I want to say is this class of singularities are very restricted. So it's very mildly singular class. So it's even like
It is required to be normal in the first one.
well, it's automatically follows. So this is automatically normal. But yeah, so simple example is like orbifold in this case, and in this case we have simple normal crossing. So and I
thought that was the canonical.
which one?
That's similar.
Yeah. So sorry, I did well this part. So I'm just assuming. So let me. Yeah. So assume X is like this. And in the study of Castability, this classes naturally appears in many contexts, and it's due to this equivalence. So if if this is non-normal, then there should be some E with discrepancy at most -1. So if you have nodal part, then this part has -1 discrepancy. So and basically, so what I distributed is a list of similar canonical singularities in 1 dimension and 2 dimension. So it's quite restricted. And in 1 dimensional case, of course, as this is normal, then this is smooth, and this is just nodal singularity.
Is it a non-log terminal, semi-log?
Non-log terminal. Sorry, say again.
You've left out the rational double points and things like that.
So rational double point is inside here.
That's what I'm saying. So you're leaving out the log terminal.
Sorry.
The list is just the strictly semi-log canonical.
Well, I wrote as orbifold. Yeah. So in 2-dimensional case, this is orbifold. Equivalent is orbifold. And like in higher dimension, just one way is correct. And so I would say this is orbifold singularities and a bit more. And this is like normal crossing singularities and a bit more. Maybe too rough, but. Anyway, I studied 4? Okay. And what I'm going to talk is another box. Another background, which is modular construction. This modular is modular of varieties of general type or more strict class. So it is like, let me abbreviate this from my own as SLC and maybe LT or something. So what we consider is SLC variety X, projective variety X with Kx positive. This means ample in this situation. And if you correct these kind of varieties, then this forms a good moduli. That is the moduli. And this is often called a Shepard-Baron. RxF theory. And the point is, this construction is via MMP. The essential idea is coming from MMP, so not GIT. So also it's naturally extend what's called the Green manifold compactification of curved moduli.
What's that word in that codimension tool? It's condition.
Oh, this one?
Yes.
Well, so let me rewrite. So I mean,
What is it called? What's in codimension tool? That word is
this one? Sail.
Oh,
Yeah,
okay.
champion sail.
Okay.
So it corresponds to Hartog's extension theory. So it's extend the famous construction of MG bar. So it's by, people often call this a good dream of compactification. But also there's some guy who, in my years, who I think he found this class of nodal stable curves. And anyway. So now we know that this construction is possible by using GIT, and then they were generalized by different method. So this is by Riemann-Ford and Giesecke manifold. Maybe Knudsen manifold. So they prove that this is a MG bar is projective. So via GIT. So anyway, so in dimension one case, this is originally by GIT and.
What do you mean by modular?
You mean precise formulation? Yes, well, I think briefly. So we consider all families of this guy. A flat project family whose canonical divisor patches in a good way. So so we consider all families like this, whose, well, not necessarily curve, but whose fibers are these projective varieties. Then, well, this modular is a universal variety to which this C has a morphism to that. So we need this concept of families. And well, there are some subtleties in higher dimension. What's the correct notion of families of these things? But yeah, I think it's too technical to touch on that. So anyway, let me talk this key idea on this construction. So the point is, for a given punctured family, like this, maybe, let me see. So, this punctured curve, then obviously all fibers sit in this class. Then we construct, we can construct, a very unique family which fills some central fiber in this missing part. With the same thing. Up to base change. Base change means so we have a C point 0 inside C, and if there's a room to take some finite cover of this, possibly ramified over 0, and we can. So this doesn't affect. So up to base change means that. And so the key point is the construction of this so bigger family, and this is construction of this X is via, precisely speaking, what's called relative MMP. So relative MMP is like, so first I think I wrote minimum model for a given variety, but there's a version of MMP called relative minimum model, which is about a variety with a morphism to some other projective variety. And then we can leave the morphism existing, and we can get some other family. And what we do is here is we take some arbitrary filling, and then which might have some very many redundant divisors inside that central fiber, and we run MMP, and precisely speaking, take canonical model of that. Then we get such a canonical limit like this. And then
When you lose varieties, everything contracts one of these divisors.
Sorry?
When you lose varieties in your original.
What do you mean by roots?
This is only over the central. This is only over the platform.
Yeah. So away from this point 0, nothing has changed.
Fiber-wise MMP.
Yeah, more or less like that. But we definitely need 5 family.
And this uniquely is a unique we require central fiber to be semi-canonical.
Okay. Yes, so sorry. The condition is like it's not very precise, but all the fibers are semi-canonical with some example. Well, a bit more precisely, we need normalization and also the Q-Gorenstein condition on the total space, not only fiber-wise. But yeah, I think.
How many curves here? Or is it
Well, in any dimension.
okay.
Yeah.
So in dimension 1, it agrees with this mg bar.
Right. So semi-canonical means just nodal and K example can be written in terms of. So it's equivalent to that. Any P1 inside that should intersect with 3 points with other components. Where I put eraser. Right. So, yeah, that's what I was trying to write. But that's my eraser. So this is saying we have canonical limit for any punctured family. So which means the modular is more or less Hausdorff and also compact, right? So the only missing part is to construct ample line bundle on the moduli, so which is a different matter. But, still, well, at least we can see that this is compact. But heuristically, I mean. Sorry, where I put my. Oh. Okay, I see. Thanks. Oh, yeah. Thanks. So there are only 20 minutes left. So I should explain. Well, what I've been explaining so far is just background, so I should write a relation with the Castability. So here's a theorem. So possibly this X is possibly singular projective variety, but satisfied, satisfying the technical condition, which I wrote as this one. Yeah, for example, like in normal case, normal one Q-Gorenstein, and then the following is true. So I'll say this is theorem A. Which I've been working for like a long time. So whenever this is satisfies this stability notion, then X must have this semi-canonical singularity. So for example, a curve case, which this means that this semi-stability implies that X is nodal. So this is due to Mumford, I think in tab 70s. And the two-dimensional case, so this is due to Shah. Precisely speaking, they have been dealing with the classical stability notion, which is asymptotic. Hilbert or Chow stability or semi-stability. Semi is fine for this case, but this implies this. So, and so the proof of this one involves MMP, and the kind of hardest. And so this naturally asks us what's the converse? What about the converse? So Carabiel case, which means this kx is numerically or like homologically 0, then this is k stable if and only if x is coterminal. So as a special case, this means that smooth case is k stable, which is corresponding the Gauss existence of K-Einstein, and semi-stability. Semi is semi or canonical. And I think I might mention a bit more about this, as there's some differential geometry counterpart on this. So recently, Valentino posted some related thing, but let me mention if I have time in the end. So for general type case, which is precisely speaking the case where L is just a canonical polarization, then this is L is K. This is also kind of equivalent. The converse is also true. And even same is enough as this shows. And actually, this reaction is easier without using MMP, just standard bilateral geometry. And what I wanted to write is these such X is exactly what is being parameterized in this moduli. And also there's some, this part is not a theorem, but kind of definition in their theory. And also there's the differential geometric interpretation of this as the existence of K-Einstein metric on the smooth part such that the volume is finite. So we take integral of this one at the smooth focus. And this is due to, obviously not due to me, but Guenancia this year.
You need this number to be the same as the intersection number. Otherwise, there will be too many of them. This is the expected volume.
I see, okay. Yeah, thanks. So I think this generalizes a hyperbolic metric on stable curves, like, I don't know, like hyperbolic. Stable curve. So So one thing I want to say is so this one. So originally this modular is not coming from a GAT construction, but so well, I thought it might be like indicating that there's a modular of k-stable things rather than the classical GAT stability stable things. So which I will explain a bit later. And well, now I think I want to give a sketch of the proof at least to a certain extent. So proof. About proof. Oh. So the key, there's a key formula for Donaldson-Futoki. So recall that this k-stability is some positivity of, positivity or non-negativity of invariant called Donaldson-Futoki. So that's the key thing, key invariant. And there's a formula to Xiaowei 1, and which says this Donaldson-Futoki is essentially A1 also intersection number. So we take compactification like this just by attaching infinite trivial fiber over infinite point. So we only have degeneration on the central fiber, so we can naturally attach the infinite trivial fiber here. Then this df, which was defined earlier, is like this kind of relatively simple intersection number. So very well, briefly speaking, it's due to Riemann law, and so recall that the definition is by considering this thing, and we consider the dimension of this one and also the weight of sister action on this one. And for the dimension, we can calculate by using Riemann law, and the weight can be seen by using the equivariant Riemann law. Then we obtain this formula, which is just intersection number. And this is quite crucial because this gives a bridge between like a canonical divisor of this total space and this k-stability stuff. So from this point of view, the Donaldson-Futoki is also like calculatable things. And so recall that so Valentino said that this Futoki is also was calculatable by using localization formula. So this df is indeed like kind of calculatable things. I even feel that it's easier to calculate rather than like classical GAT weight. So anyway, or if you wish, you can regard this as a definition of k-stability by using this and say that k-stable is the positivity of these guys. although it's a bit natural way to say. And well, another thing I want to say is so there's a line bundle called CM line bundle, which exists on any base of a polarized families. So in this case, we have CM line bundle on P1, and we can take degree of that, and it's coincide. So this is a part of his theorem, and so. Yeah, this is called CM line bundle. I think, well, this name and the general definition is due to Paul Tian. But the first paper, I think, is treated in higher dimension is Fujiki Shuma, I guess. Oh. Maybe I should have said that this the general fiber of this polarization was supposed to be L to the R, but so we are assuming R is 1 here. So
this equality is for the answer to taking that.
Sorry? Yeah, these are yeah, this is the same. Yeah, so this is kind of important line bundle. And so I should, well, I only have 5 minutes more, 6 minutes. So I think so about the proof. So there are 2 directions basically. So to prove stability from some condition, like so log terminal Calabi-Yau scale stable, or like similar canonical. Canonical model is scale stable. It is due to so blah 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 Imperial stable or semi. So this is just by estimating df via the formula. Or this is just uses standard variational geometry. So not MMP. And so the much harder part is number 1. So and I think it's much deeper. So let me explain that part. So the idea is consider some idea. Consider idea like this. In x times c. So here we have x and multiply by a1 or c. And this form of ideal contains this. So should be inside t equals 0, at least theoretically. So should rise like here. And what happens if we blow up this one? Then what we get is blow up. Nothing but just configuration. I'm sorry. And as polarizations, we can consider pi star p1 star L to the power R minus E. So E is the natural exceptional divisors coming from this blow-up structure. So maybe we have exceptional divisor like this. Then what we do is take the asymptotic behavior, or consider so the leading coefficient of this df of the same this thing. So note that there's r here with respect to r. Then what appears something like is, so the leading coefficient is L to the, sorry, let me write this as L. Then maybe I shouldn't, because I used in that part. So pi star p1 star L S dot minus E dot n minus S times KB minus X times A1, where S is the dimension of subplot. And this is the same as the leading coefficient of other thing, which is of just pi star p1 star L to the R minus each so this thing. So probably don't need to care the detail, but anyway, so what we have here is the discrepancy. So this discrepancy of this birational morphism. So what we need is to if there's some J with this birational morphism or this discrepancy, not if anti-effective, I mean, with I wrote the coefficient as AI, so AI negative, then X is L is K unstable. And for the construction of such J, whose origin lies in a paper of Shah around 80. So the construction of J which is coming from construction of I0 and which is similar to construction of blow up those guy. Oh, this is quite big, but so we do take some model and take semi-canonical B such that this KB over X is relatively ample. And such a model was constructed by myself and Jun Shu. So this is quite.
I was going to ask, then that gives you actually that X has to be just canonical.
Because you're not using S smaller than -1, you're just using S smaller than 0.
Yeah, sorry. So the idea is, sorry, so I think I should have mentioned earlier. So we are assuming this is not semi-canonical, then trying to construct.
Yeah,
Yeah,
that's
events.
what I want. That's what I'm trying to say is that wouldn't you be able to prove with this much more? And
What you mean?
well, if it's not semi-canonical, then you have something that's smaller than -1. No.
So there's a bit subtle issue. So this one is a discrepancy of one-dimensional. Yeah, kind of a junction. Yeah, well, this is actually 0 plus t m, and take power and take integral closure. So and this n is corresponding to manifold semi-stable criteria. Sorry, I'm rushing, but anyway, so essentially we are using MMP here. And so we construct, for starting from non-semi-canonical variety, we are taking kind of semi-canonification, minimal semi-canonification which exists by using a minimal model program like this. So it's analog of minimal resolution. And then we are putting this into the central fiber. Then somehow we can control the discrepancy, and then the DF is becoming small and small. So this is very vaguely like indicating like if we use minimal model program on the central fiber or even like total space, then we are getting a small DF, which appears in different contexts later as well. So let me just finish with half more board, which is about the next talk. So the section 5. General conjecture I have in mind is what I'm calling K moduli. So that's about moduli of K stable things. And well, I haven't fixed all the precise details, but what I'm think now. So this is a temporary formulation. So moduli function of K semi-stable polaris varieties have categorical moduli variety of scheme, which is and there's some line bundle which is exactly the same line bundle there. Descend on it as a ample line bundle. And so that this should be at least Kaji projective on each component, and so this is joint union. Projective schemes. And so what I'm explaining later is the work with Sonson and Christian Spotti for the repeated case on this moduli. with different perspective from Gromov house of distance, as was in Crow's talk. So, so this K ample case is corresponding to this MKSBA, but it's well, personally I was motivated by this one, but it's also coming from differential geometry. It's compatible, I mean, background and also like so. Yeah, I suppose in the Crow's talk and Valentino's talk. Also, what Crow's talk talked was there's a Gromov house of distance, which makes this kind of moduli of varieties with canonical metrics, Hausdorff, and Valentino almost explained in this Fujiki Donaldson's picture, which also explains roughly like this. Or some technical difficulties which is not settled is like what's the meaning of polarization? Maybe we need to consider like cohomology or equivalence of that. And varieties, what we mean by variety, we need some condition, the singularity as with this. What I wrote a star. But my observation is that at least K ample case, this coincide. Also the GIT is not. Yeah, so I think I stop here.
In your theorems, is there any examples that show you couldn't replace K stability with Hilbert stability or Chow stability?
Well, I think that's what Chow Weber is going to talk. But so for example, like
The answer is yes, and I'll just wait for his talk. I'm just curious.
yeah, well, Hilbert stability, not asymptotic. So it depends on how you formulate.
Asymptotic Hilbert stability.
Yeah, then so as asymptotic stability, well, semi-stability implies like K semi-stability, and this should be yeah, semi-canonical, but well, but I think what Shaway is going to talk is essentially giving non-compactness of asymptotic things. So at least know that asymptotic things should imply K semi-stability. So at least if you stick with a class like this one, then yeah, we have modular of this one, but not this one. So there are many. Yeah, I think the first one was Schiffer's pattern.
Okay, since we are lack of time, so we will have 5 minutes break. Thank you, Yuji again.
Giving